Fe doping enhances the peroxidase-like activity of CuO for ascorbic acid sensing. Welcome to Journal Club. The latest academic research, explained in plain English. Today we're looking at this paper from MDPI's Journal of Chemistry. It's authored by Yan et al. From Hunan University in China and is published open access under a CC-BY license. Let's start by translating the title into more accessible language. When you read this title, you can understand it to mean in very simple terms that adding iron to CuO improves its ability to detect ascorbic acid by increasing its ability to mimic the activity of an enzyme called peroxidase. Let's expand on that a little. This paper explores how adding a substance called Fe to copper oxide, CuO, makes it better at detecting a type of vitamin called ascorbic acid. This is because the Fe-doped CuO has a stronger ability to act like an enzyme called peroxidase, which is important for detecting ascorbic acid. Now we understand the title, which is a good start, but before we can break down the full paper, we'll need to catch up on some terminology, jargon, background information and context. Specifically, there are some key concepts you'll need to be familiar with. Let's define them now. Nanozymes. Synthetic nanomaterials that mimic the structure and function of enzymes. Peroxidase. An enzyme responsible for catalyzing reactions involving hydrogen peroxide. CuO, copper oxide, a type of metal oxide commonly used in nanomaterials. Fe doping, introducing iron atoms into a material to modify its properties. Redox reaction, a chemical reaction involving the transfer of electrons from one molecule to another. Coprecipitation method, a method of synthesizing nanomaterials by mixing solutions with the desired components and precipitating them out of solution together. Chromogenic oxidation reaction, a reaction that produces a colored product as a result of oxidation. 3,3,5,5-tetramethylbenzidine, TMB, a chromogenic reagent commonly used in enzyme assays. Visual sensing platform, a method for detecting substances that produces a visible signal. Limit of detection, the lowest concentration of a substance that can be reliably detected using a given method. Now that we understand the title and key concepts, we're ready to dive in and break down this paper. In this presentation we're going to attempt to answer 5 questions. 1. What were the researchers trying to figure out? Or more specifically, what was their hypothesis? 2. How did they conduct their experiment? That is, how did they test their hypothesis? 3. What were the results of the experiment? 4. What conclusions did the authors draw from those results? And lastly, 5. Why does this research matter? Why should you care? 1. What were the researchers trying to figure out? The researchers hypothesized that Fe doping could enhance the peroxidase-like reaction rate of CuO nanostructures, leading to a higher enzyme-like activity for biosensing applications. 2. How did they conduct their experiment? The researchers prepared CuO and Fe CuO nanostructures using a coprecipitation method, characterized their morphologies using a transmission electron microscope, and recorded X-ray diffraction patterns to study their morphology and structure. They measured the peroxidase activity of undoped CuO and Fe CuO nanozymes using the catalytic oxidation of TMB with hydrogen peroxide and studied their kinetic parameters using the Michaelis-Menten equation and its Lineweaver-Burke double reciprocal representation. They also detected ascorbic acid using Fe CuO nanozymes and calculated the limit of detection. Finally, they performed a total antioxidant capacity assay on a commercial beverage and conducted spiked recovery experiments to calculate the recovery. All chemicals used were of analytical grade and ultra-pure water was used in the experiment. 3. What were the results? The researchers' results showed that Fe doping enhanced the pod-like activity of CuO in the proposed Fe CuO nanozyme. Further analysis of the kinetic parameters of CuO and Fe CuO nanozymes showed that Fe CuO possesses a stronger affinity to H2O2 in comparison with CuO. Reactive oxygen species were also investigated to confirm the catalytic mechanism of the Fe CuO nanozyme. The platform for H2O2 detection achieved higher sensitivity. 4. What conclusions did the authors draw from their results? The researchers discovered that by adding iron to copper oxide, they were able to create a more effective nanocatalyst for detecting ascorbic acid. This new platform has a limit of detection of 4.66 m and high anti-interference capabilities, making it an effective tool for detecting ascorbic acid. The research also provides a new method for creating effective biosensors. 5. Why does this research matter? This research paper is important because it presents a new strategy to enhance the enzyme-like activity of nanozymes, which can have potential applications in biosensing. This work provides a new method to prepare effective CuO-based nanozymes with improved catalytic activity, which can lead to the development of more high-performance nanozymes for biosensing applications. We hope you've enjoyed this journal club presentation of fade doping enhances the peroxidase-like activity of CuO for ascorbic acid sensing. If you'd like to read the full paper yourself, which we encourage you to do, you can find it at DOI 10.3390/chemistry 50200088.